So chapter 6, I want to take that one yet. Instead, I will show you some slides stolen from this Italian guy, Joel Guerrero, who has a little bit more, say, open form practical approach to the whole problem. So here I just call this one for finite volume. He describes it yeah, fairly okay, I would say. So this could actually have been a better way to understand the open form than the book by Versteeg, but never mind, we have both. I'll just go through them a little bit quick. So this is sort of the initial equation, the place to start, so sort of the original, everything here, volume integral over your finite volume. And what we do, we have to discretize our space into nice little volumes, and the volumes, as we now know, has to be convex, but it can have any number of faces. Here, well, it's not so easy to see maybe, but when you have a region in space and you divide up your space into cells like this, then typically you will do something like this, another cell up here and so on. So one face, he will be part of two different volumes. And that's very convenient when you are calculating the fluxes back and forth these cells. But nobody has said that this has to be the case. We could have made a gap here, and then we have another cell over here. So they are not directly linked to each other. That would be possible. Of course, we have to handle this gap a little bit differently then, of course, but it would be possible. This is not so common. What actually is common is you have a mesh coming something like this. They overlap a little bit. That's actually happening, well, not frequently, but yes, it happens. Say you have some moving mesh, one part is standing still, the other mesh system is moving. Okay, then we have to start interpolating here to find the values, but it can still be done. So don't limit yourself to say that, oh, they have to be face to face all the time. No, they don't. They don't have to. Here, of course, center point, that is where we have our unknowns, but then also we need to find the angle here. And depending on the geometry, he can be more or less messy, unstructured. So you can have different angles depending on the orientation. I mean, if you have the center point here, then these faces, they can, does not necessarily have to be 90 degrees on the line towards your center point. They can have any angle actually. So this is something that we have to take into account when calculating the fluxes. So then we can now jump from our volume integral and now use the divergence theorem and rewrite it as surface integrals. And this then actually is done with all terms except the source term. This one will still be a volume integral, but diffusion, convective flux terms will now be surface integral. The time derivative we haven't really discussed yet, so we will wait a little with that one. So here, how to approximate these surface integrals, and in practice then you end up with a sum of fluxes throughout your phases for all the faces in one single volume, of course. So you end up with algebraic equation in the end, of course you do. And the question then is, of course, how to do this modeling here. So you might say the first step, the volume integral to a surface integral, that one is exact, nothing wrong with that one. But then from this integral, finding the sum of and how this one then is modeled or interpolated or discretized, that's where we have our question, how should this be done? Same with the diffusion terms. Source, okay, we normally split him up into two possibilities. He has a constant term that will then be just a constant multiplied with the volume, but he may also have some changes with the center point value, depending on the center point value. So it's just a linear variation of this source term. May happen, but normally just a constant like gravity. Yeah, a gradient term, not so interesting or difficult. Finding the gradient of the pressure, no big deal. So this is roughly what we have so far. And yeah, I won't go through all the detail here. Convective fluxes. So here again, now a discussion with how to find the convective approximations. Central scheme, first order upwind, linear upwind differencing. So linear upwind, that's second order accurate. So we have several schemes here as well. And again, more advanced schemes, more modern schemes, total variation diminishing. And the same discussion here with this limiter function, the psi function. And also he does a lot of discussion where it might be, where it should be, and so on and so forth. And you see the same example here. This advection equation example. You have initially signal looking something like this, and then you let him move in time. So the correct solution should be this straight lines where you jump from 1 to 0 instantly, and it shouldn't be smeared out in space. But now, depending on your upwind schemes, well, some effect of smearing is unavoidable. Now remember, the central scheme is not an option here. It will explode. It's unconditionally unstable, so we have to do something like this. Now, for this example here, the super B limiter looks very, very nice indeed. Min mode, van Leer, not so well for this case. Upwind, first order, you see, is quite awful. He really smears out everything. Way too much viscosity in the problem. And if you had continue, everything will just disappear. Linear upwind, second order accurate, much better, much better. But not so stable. Because that was the nice thing with the first order upwind. He was unconditionally stable, at least for the pure advection equation. So the other schemes, they will be more jumpy, but at least possible to find a solution. So yeah, more or less nice. The best one for this case, the super B limiter, turned out to be quite nice, I would say. So here you see the first order upwind scheme all the way down here. Quite awful actually, but very stable. So if you now start messing around with your grid, it's not rectangular anymore. You get some angles. Okay, then this has to sort of be corrected. We have to take some mesh adjustments into account as well. So we don't have to go into all the details here. You have the same also with the diffusion schemes. If you have an angle here, okay, you will get additional terms. Of course we will, due to the non-orthogonal mesh that we now have. And how this can be corrected, we will address, I think, in exercise 5. So there you will see the effect of non-orthogonal meshes. And also, yeah, the diffusion fluxes has to be corrected then, non-orthogonal correction. And other errors as well. The temporal discretization, the time derivative, well, we can have a peek into it here while we are at it. So we will still need to address this time derivative if we are looking at a transient code. You want the time development as well as the spatial solution. So yes, we have to do something here with actually the entire equation. So now it's a question how to take a time integral. One thing is the time derivative itself, fair enough, but also the other ones has to be decided at what time level should we take the values here. How should this be done? And well, we have several options to do this. So far you have only been seeing the first order Euler scheme. That's very simple. We have also talked about the first order backward Euler scheme. That's fully implicit schemes, but we have others as well. We will address these later, I would say. Also, this linear system solution. So now you are talking how to solve these huge algebraic equation systems. How can this be done? So this is also something we are going to address later. So finally then, let's see what OpenFOAM does in these files. Well, we have discretization, and well, for this version of OpenFOAM, it's version 3 something. The block mesh dict file was inside the constant pooling mesh. Now it's moved, we find it in the system folder, but else it will be the same. Physical properties we find in the constant folder. So far we have only looked at incompressible flows, and the only property then it will be the viscosity. And now discretization schemes. So here you have sort of the layout, the stencil for the FV scheme file, as I showed you earlier. So time derivative. Here the default is set to be a backward. That would be the first order backward Euler step, fully implicit. Gradient schemes, just a linear. Everything here is Gauss. He turns up all over the place. What's this? The Gauss. Well, that's the divergence theorem. So you go from a volume integral to a surface integral. So that's why Gauss is all over the place here. The gradient schemes, only linear, and also the divergence linear. No problem with these. So the question is this gradient schemes where we had, where is it? No, this one. Yeah, sorry. Divergence of the sort of the transport there. How this one should be handled. So here I've chosen a linear, Gauss a linear. That's not recommended, I would say, because then you are talking about central scheme. So he will be very, very unstable. Different time schemes. We will have a look at these later. But Euler, first order Euler, and then the first order backward implicit. Those are the two we have seen so far. Well, actually also this steady state, and we don't care about the time development. Yeah, I want to have a look at these. Now, here, it's sort of the most popular discretization schemes when it comes to the convective terms. How should we do this? So, upwind, first order, should never be used unless you use it as an initial, to find an initial solution to stabilize things. Linear upwind, that's the second order accurate. That's not so stupid. Pure linear, be careful with that one. It can explode. That's the central scheme. Muscle, more advanced. Quick, more advanced. Super B, very good. And then, and so on. So this is models that you may choose to use. Some might be very good in some cases, some might be very bad in other cases. So you really don't know. You have to sort of test it if you are running a case that nobody has ever tried before. Then you risk blowing things up. So a very good idea then might be actually to start with this very bad one, first order upwind, just to get a solution and see what's going on, and then try from with this solution as an initial state and see if you can use one of the more advanced. Of course, you want to have at least second order upwind schemes in the end. So here also you can see the first order upwind, only first order accurate. It will be bounded, so no problem there. The linear, that is the central scheme, second order accurate, unbounded, very unbounded indeed, going to explode. But the other one then you see more or less bounded. Not this one limited linear, unbounded, but still more stable than the central scheme. Yeah, linear upwind. So you have to use also the gradient of the velocity has to be calculated somehow. So inside the divergence schemes here, a linear upwind, he's going to need this one as well, and then you have to tell him, okay, how should this one be done? And then you could choose different gradient schemes here as well, more or less advanced. So you have several options to construct or choose the different schemes for your open foam version, you might say. Different gradient schemes. All of them second order accurate, so there shouldn't actually be any point in playing around with anything else than the standard Gauss scheme, but sometimes it might be a point. Yeah, also here gradient limited. I won't go through all this. Some may introduce additional diffusion, and that's not necessarily something that we like. So the less diffusive, the more accurate. But sometimes we have to really slow down the process here, slow down the solution to avoid that the solution explode in our face. But we never know what is correct for one case to the next. So sometimes we have to actually play around with these. Normally you won't touch them at all, but just be aware they exist, even for grabbed schemes, not just for the possible upwind schemes. I won't go through all this. So, for instance, I set up here with quite accurate schemes, but a little bit dangerous, a little bit oscillatory numerics, meaning it might easily blow up in your face here. So here you have fully implicit scheme. That should be stable, straight, linear, central space for the gradients, the divergence div scheme. Here it says Gauss linear, that's second order, but the central scheme, very jumpy, we know that. And here linear upwind default should be okay, I think, for these. That's K omega, so yes, it's a turbulent case he's running here. And the rest just the standard linear, yes. So yeah, I would say very jumpy scheme he has chosen here. And the main problem then is this one, phi u, linear. That's a central scheme, dangerous. Less accurate, but quite stable. Okay, you have gone to a linear upwind. That's second order, but it's an upwind scheme. So this will be definitely more stable. And here, a very stable scheme. Okay, then you see first order upwind for all of these. Very stable, yes. But you will have an answer which is terrible. So here, as he says, play with these and you will succeed. Yeah, the Courant number here, we can have a talk about it. The Courant number, yes, we have discussed this earlier. Physically, it means you should not travel longer than one single cell length throughout one single time step. And that will be regardless of cell. So if you have, say, a very small cell somewhere, and then we go all the way down here. So we have a very tiny little cell down here. And this is in a location where you have a very large velocity, then you're in trouble, of course. You are not allowed to travel longer than 1 delta x over one single time step. Because when we do the calculation here, all the fluxes, what comes in to a cell, what goes out to a cell, we normally only take into account the neighbor cells. We don't look at the next neighbor. So for this cell here, to find out, okay, what comes in, you look at all the fluxes around you, but you don't pay attention to what comes from the cell far away. That's not into your schemes. So in general, we would say the CFL number has to be 1 or smaller. And you have to check it for each and every cell, for all the local velocities and the local cell sizes, and in all 3 directions if you're doing a 3D case. So it's sort of tedious to check, but we have no option, we have to. You have other schemes that actually take the next cell into account, and you have schemes where he's so stable that he can manage Courant numbers bigger than 1. He doesn't give you a good answer, but he can still handle it. So normally, in general, I would say Courant tau CFL number of 1 or smaller. So here, pure explicit method, using the solution at time level n minus 1 to find an explicit expression for the solution at time level n. While implicit, then you sort of go the other way as well. You are here is a mix things solution for time level n minus 1, but also the new unknown solution at time level n is involved in finding the solution for this unknown. But of course then you have to solve an equation system to find it. And that can be hard. So implicit methods involve much more CPU, much more calculation, but they will be in general more stable. So and they should be used with care. I think I showed you some of the danger with implicit methods. If I recall correctly, we used as an example the startup of a cuvette flow, and the laminar solution, as you all know, is a straight line. So this velocity profile is what you should get in the end. But in the startup process, the equation describing this problem will now be time derivative equal viscosity and double derivative with respect to, say, y in this case here. And you start then initially with the velocity equal to 0, and at time equals 0 you start the top wall, and then the solution should tends towards the steady state as time goes by. And this, yes, can be done nicely, easily, if you now use as first order Euler step, no problem, but then you have to use a quite small time step. If you program it using implicit methods, then you could take actually as big time step as you like. But you could get a solution that could actually look something like this. You could get totally crazy solutions. Remember, it's still only a first order accurate method in time. So, meaning you have an adder of order delta t. Okay, if you choose a large delta t, you get a large adder. It goes without saying. So, implicit methods, use them with care. You can get very stupid results. Where they actually are very nice, that is, I'm only interested in the steady state solution. I'm not interested in the time development. Okay, then I could have chosen a steady state solver like simple form, but I could also chosen an implicit method and taken a time step for 1 year or 3 years. Then you take a very big time step into the future, finding the steady state solution more quickly. That is actually an option. Else, implicit methods used with care. You might also say, if you are really interested in finding the time development of a problem, I mean, in Mother Nature, you have a lot of time varying problems, like what we are going to do in exercise 5, for instance. You have this nice Taylor vortices behind a cylinder. That is something built into the Mother Nature. So we just have to solve the Navier-Stokes in time and space to find it. If you had chosen an implicit method there, you could have taken time step quite big. So big that you actually skip the physics. I mean, remember this frequency, that is something that Mother Nature decides. It's not for us to decide. And then if you take a very big time step, then you don't see this frequency at all, or you get something very, very, very wrong. So, implicit methods, careful. Yeah, I won't go through all the details here. Here's some personal approaches here of the Courant number. So how to control it? Well, in the control dict file in open form, you have to specify then a delta t if you are running a transient code, like icofoam. Simple form, if you check, then it says delta t is 1. That's to tell OpenFOAM that I'm using a steady state code. I don't have a transient code. Then you use delta t as 1, and you use then time as an iterative dimension. But here, a real transient solver, then you have to set a number for the time step. What should this number be? Well, that number, the delta t, should be so small that you get a Courant number of 1 in the end. So a little trial and error. You have some options down here actually to have some automatic adjusted delta t so that the CFL will be under 1 automatically, or under control at least. That's actually an option. Yeah, I won't go through the details, but then when you simulate, you get the printout, and then you get the average Courant number and the maximum Courant number. So that's something then you have to look into. You risk running a code where they have set up this automatic control for the Courant number. Then you have to be careful. You risk that they create a delta t that's going smaller and smaller and smaller, because say you have done something really stupid. Something really stupid like let's try to do something very stupid here. I have an inlet here and I send in a constant velocity. Then I forget the outlet and it's incompressible flow. Of course, this is not possible. And I demand the velocity here is said to be 1. Okay, then he will do it. He will try. But of course, this will explode. This is not going well. But if I had programmed it or chosen here a system where he automatically should adjust the time steps so it still should be stable, then actually he will try. But then you risk wasting a lot of CPU time sitting there watching your computer simulating, but then you have a time step of 10 to the minus 10 or something in seconds. So it's going to take forever to obtain a solution, and in the end he will fail anyway. So if you're using these automatic time adjustments, be aware. You should have a peek at it. It might not be so easy when you are simulating, and this information here from OpenFOAM is just scrolls over the screen. It goes fast. Then you have control, what is it? Control S. He stops it. He will stop the scrolling of the screen, but also he will stop the execution of the program. It's just a pause. He doesn't break it. But that gives you an option to have a look at what is all these numbers, especially what are the Courant numbers here. Will this go okay? Also, what's my time step now? Is it going smaller and smaller and smaller, or what's happening? So Control S to stop the scrolling. And if everything looks okay and you want to continue, Control Q. So Control S and Control Q, they are nice to know when you want to stop just the printout of the screen. Also, of course, you should have a peek at all these residuals. All these numbers should be smaller and smaller and smaller. Residual, that is when you write your equation, one term plus another term plus a third term equal to 0, and then during the iteration process you won't get 0, you will get a residual, but he should be close to 0 when you have hopefully solved the equations correctly. So have a look at all these residuals, just a quick glance that yes, they are closing in on 0. We will have more information later what this means. They are actually part of the solution process. That's the other FV file, the FV solution file. So more of that later. Yeah. So here he has been playing around with different test cases, and as you can see, even Courant number 5, Courant number of 10, it still doesn't blow up. So it's possible here to choose so stable schemes that yes, you can do this. It might be stupid, but you can still do it. Yeah, I won't go through all this. Okay, that was a little practical approach then towards OpenFOAM. I'll copy out this finite volume presentation by Joel Guerrero on the homepage, so you can find it there. Any questions from you? Okay, then we stop here.